So for this video, I'm going to talk about determining if a set is a vector space. So I'm going to go through these three examples. And you can pause the video to read these over. I just want to remind ourselves, what is it that we need to do to prove whether something is a vector space? So to prove something is a vector space, it's a little bit of a tedious process. So V has to be a non-empty set of objects that would be called vectors if it's a vector space, with the operations of addition and scalar multiplication defined. And to prove something is a vector space, you have these 10 vector space axioms. So you have it's closed under addition, commutative under addition, associative under addition. There's a zero vector. There's a negative vector. It's closed under scalar multiplication. And you have all these other scalar operations that you can do. So I'm assuming that you're familiar with the vector space axioms if you're watching this. I'll just go through this one more time, and you can pause the video if you want to read these over or write them down. But so we have to prove these 10 axioms to prove something is a vector space. So it's a little bit of a tedious process. And very often, when you're first learning about vector spaces, you will have to actually prove all 10 of these. So it is a tedious operation, but it's a very good way to make sure that you understand how to prove something and to really drill these axioms into your brain. Now, we have a set of general steps to prove a vector space that helps, I guess, shake out if it's not a vector space a little faster. So the general steps for vector space is 1, to identify what your set V is and what the vectors are. And then step 2, identify what the addition and scalar multiplication operations are. Okay, so this is actually very important to discern between these two things. I think sometimes this can really confuse people, and I have a really good example of this as we go through. So hopefully we can make a little more sense of that. Then we have verify the set. Verify the set is closed under addition, axiom 1, and closed under scalar multiplication. So that's the next thing that you want to do. And then finally, you want to confirm that all other axioms hold. So if you have a vector space, you do have to actually go through and confirm all of these. And sometimes you might find that axiom 1 and axiom 6 hold, and then it's like some other goofy axiom that does not end up holding, and you don't figure it out until you've gone through them all. So it is a tedious process, but it is an important thing when you're first learning this. Okay, so let's start with this first one. And this one's actually a challenging one. So I think this is a really good one to wrap your head around some of the axioms if you feel like you're struggling with it. So I have V is the set of all ordered pairs of real numbers. Okay, so this is step 1, right? Identify what the set V and what the vectors are. So in step 1, V is just a set of ordered pairs. So U is U1, U2, V is V1, V2. These are just real numbers. And so then it says, define U plus V to be VU1 plus V1 plus 1, and U2 plus V2 plus 2, and then KU is KU1 and KU2. So this is like normal scalar multiplication. So the normal scalar multiplication, since this is how most vector scalar multiplication would work, or like the normal typical vector space would work, the standard operation, this we already know is closed under addition. This is a little more interesting, and I think this is a really good way to start wrapping your head around how to prove something as a vector space. So this is what the operation of U plus V is, right? This is not the form that your vectors have to always be in. This is just what you have to do to add two vectors, okay? So as long as when you do this, you end up with an ordered pair of real numbers, then you are good to go. So I bring this up because, you know, the first thing that we need to do is prove axiom 1. And so just taking a look at this right here, U1 plus V1 plus 1, there's nothing that I can put in here that is not going to result in a real number. Same thing with this, U2 plus V2 plus 2. There's no choice of U and V that when you add the three together, you're not going to end up with a real number. So axiom 1 is closed under addition because any choices of U and V will result in an ordered pair of real numbers. That is what we have to confirm. So we're good to go there. That's just the nature of these calculations and using things that I know about real numbers. And then similarly, KU. So KU is really like standard scalar multiplication. So K times any real number is going to be a real number. So this is still going to be a real number. And again, that's what we're trying to confirm, just that it's a real number, not that it looks like this. Okay, so let's clear all that out. And now let's talk about some of the other axioms that might be a little more confusing or messing with your head a little bit. So the first axiom I think of that I think might mess with people is the one with the zero vector. So a zero vector is defined as a vector that behaves like this. And we mark it as the zero vector, but I just want you to note that the zero vector does not have to equal, so it does not imply that it equals 0, 0. Now, if this were the normal, like R2 space of just two real numbers, and we just do U1 plus V1 and U2 plus V2, so if this operation were defined like we would normally think of, then sure, this would be the zero vector. But actually in this case, this isn't going to work out. So notice what happens. So if I take, let's take 0, 0 plus, I'll take V1, V2. Okay, so I am now going to just take this. This is my first vector. This is my second vector. So if I add these two together, I get 0 plus V1 plus 1. And then I get 0 plus V2 plus 2. So that is what this operation tells me to do. And so then, of course, this is just going to be V1 plus 1 and V2 plus 2. Okay, so notice this does not behave in the way that this needed to behave. If this were truly the zero vector, I should have gotten back to my original vector. Oops, and I should have written an equal sign here. Sorry about that. Okay, so this should have been equal to just U. So this does not equal V1, V2. This equals V1 plus 1, V2 plus 2. So what that tells us then is that we actually have something else that must behave as a zero vector, or there is no zero vector. Now, I just have to think about what numbers would I have had to put here and here so that I would have ended up with just V1, V2. And you can see from how this calculation is set up that really what I need here is, so for me to just end up with V1 and V2, I would need a -1 here, right? Because then I'd have -1 plus 1, and then I'd need a -2 here, so it'd be -2 plus 2. So let's try that out real quick just to confirm. So I'll make some space. Okay, so now what I'm going to do is I'm going to take -1, -2, and then again I'll just take some random vector. I'll just call it V1 comma V2. So let's add these. So this becomes -1 plus V1 plus 1 and -2 plus V2 plus 2. So now when I add these together, I get V1 and V2. So what I needed, right, was I needed something that would get me back to my original vector. Boom, 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 boom. Cool. Okay. So this operation works. It doesn't matter if I do V1, V2 first or second. You can confirm that on your own. So what this means then, in the way, because of the way that I have defined this vector operation, -1 and -2 are actually the zero vector. So I'm going to note that. So in this world, my zero vector is -1, -2. So I've identified that vector, and so yeah, we're good to go on that. So far I haven't broken that this is a vector space. Now the other axiom that might mess with us is this idea that if I have a vector of U, I have a negative of it. And so now, keep this straight, right? So U plus -U has to equal the zero vector. This is the general rule, but what is 0 in our world? In our world, 0 is -1, -2. So now I need to figure out what would my -U look like so that I end up with not 0, 0, but with, remember, this vector here, because in this vector space, in this world, this is what stands for my 0. Okay, well, I think that you should spend a second here playing around with this and setting up an equation. So you need to come up with a U1 and a V2 that will equal -1, -2. And remember, this is the operation that you have to use. This is really just an algebra exercise, and it's not like a difficult algebra exercise. It's not linear algebra. It's like really just algebra. But this is something that can kind of mess with your brain. And I think it would be a lot better for you to pause the video and play with it for a second versus just watching me do it right the first time. So give it a try. Come up with what you think a U and a -U might look like that would equal this, and then hit play when you think you've got it. Okay, so in this case, so for my my u, okay, so I'm gonna take a vector u1 and u2, and what I'm gonna do, so let's see, I'll take my u1 comma u2. Okay, so when I add these together, I need this to now equal -1 and -2. So my negative u vector, believe it or not, is going to be -u plus 2, let's see, -u1 plus 2, and -u2, let's see, sorry, it should be -2, and then -3. There we go. Okay, so now I need to add these two vectors according to this rule here. So I take u1 plus this plus 1. So let's see. So I'll add these together. This becomes u1 plus -u1 minus 2 plus 1. So that's this first part. And then u2 plus -u2 minus 3, and then I need to add the plus 2. So now that's this part here. So if I add these together, now I have -2 plus 1, so that's -1, and -3 plus 2, so that's -2. And now I got to the 0 vector. So this, let's see, my -u is going to be of the form -u1 minus 2 and -u2 minus 3. So also the negative vector axiom holds here. It's just kind of goofy because of how this operation has been defined. So let me clear a little space, and so let's actually talk about which axiom fails now, because I think this is kind of a tough vector space to start with. There are a couple axioms that fail to hold. I would say that I think you should pause and try to find them versus me showing you what they are, and then hit play when you think you've gotten it, because then you'll get more out of the video. Okay, so the axiom, one of the axioms, I'll just show one of them, and I'll tell you the other one that doesn't work also, so you can try it. So the axiom that's going to fail to hold is actually this one. So I take two scalars times my vector u. So, okay, this would equal ku1, oops, just ku1, sorry, no, k plus m u1 and k plus m u2. So there is that axiom, or there's that first part, right? Now, let's see, I can rewrite this as, I guess I can just rewrite this as k u1 plus m u1 comma k u2 plus m u2. Okay, so there's the first one. So now what our axiom says, so I'll just remind you which one I'm going with here. So I'm looking at axiom 8. So this operation has to equal the same as this operation. So now I need to do the right side. So if I do the right side and I set that up, so I'm going to have k times u plus m times u. So this is going to be ku1, ku2 plus mu1, comma, can't write today, mu2. So now I have to add these two, but when I add these two, now I have to use this defined operation. So when I add these, this becomes ku1 plus mu1 plus 1 and ku2 plus mu2 plus 2. And now you will see this and this are clearly not equal because this has the additional plus 1. So what that means is k plus m times u does not equal ku plus mu. So this is not a vector space. I'll just write now to VS. Okay, and I'll also just mention axiom 7. You can also pretty easily prove that that one's not going to hold. So you can try that one on your own. same idea, and I would recommend just proving that to yourself if you're struggling with these. Okay, so let's keep going. So next I've got the set of all ordered n-tuples of real numbers that have the form 2x, 2x, 2x with the standard operations on Rn. Okay, so for this one, notice, like, I also want to just point out why is this different from the previous one. So this is telling us what the n-tuples have to look like. They have to look like this no matter what. Versus the previous example just said has to be an ordered pair of real numbers. So it didn't have a statement on what the form has to look like, okay? So this is telling us now that the n-tuples always have to look like this. So step one is, remember, we need to just identify what our vector space is. So it's 2x, 2x, 2x all the way down. And we just have the standard operations on Rn in this case. So we know how those work. Okay, so, all right. So if I take u, let's say that my u is going to be this 2u, let's see, so on and so forth. So my u is going to look like this. And my v is going to be 2v, 2v, so on and so forth. Okay, so if I take my u plus v, see, I cannot write today. I don't know what's going on with me. So if I add these together, so what do I get? I get 2u plus 2v really all the way down, right? 2u plus 2v, which of course can be written as 2 times u plus v. So that fits the form, right? So we're good to go on. So it's closed under addition. Okay, so let me make some space. So the next thing that I'm supposed to do in my general steps is just show that it's closed under scalar multiplication. So if I take k times u, this will be k times 2u, k times 2u, so on and so forth. And this is all good because this is still in the form, right? Because I could just rewrite this as 2ku, 2 times ku. So this still follows, boom, this form here. So we're good to go. So we are closed under scalar, I'll just write multiplication. Okay, so let's keep going. So now that I've shown that my vector space is closed under addition and scalar multiplication, now what I have to do is I have to go through and prove all of these other 10 axioms. So I'm just going to go one by one. So let's see, I guess I'll start with 2, 3, and 4. So I have to prove it's commutative by addition, associative under addition, and that there is a zero vector. And the zero vector still has to be in my vector space. Okay, so let's go through each one of those. So this is going to be a little tedious, but I am going to take the time to do all of this. So remember, here's my u. I'll just write out my general v. So if I want to show that u plus v equals v plus u, so I can just write out what this means. So this will be 2u plus 2v all the way across. And that will equal, or does it equal, 2v plus 2u all the way across? So the answer, of course, will be yes, since like this and this are a real number at the end of the day. These are just going to be commutative, so these indeed are equal to one another. So each 2u plus 2v equals 2v plus 2u. So you can say that axiom 2 holds. So I'll make some space. So next we're going to have associativity. So let's see, I guess I'll have this third vector w. I'm not going to write out the third vector w because it's just going to be similar form. So I just have to show that these things hold. Okay, so if I take, so let's start with, let's see, I'll do this side first. So if I do this side, So this will be 2u. So I want to add this vector to the vector of v plus w. So I'll just go ahead and write out what does it mean to be v plus w. So that's going to be 2v plus 2w all the way across. So if I actually go through and add these together, what do I get? I get 2u plus 2v plus 2w. I get this all the way across. And of course, this still fits the format because I can factor the 2 out for each one of these n-tuples. So, okay, so this is what one side equals, okay? So now I'll do, I'll do the other side in green, so I gotta make myself a little room. Okay, so now I'm gonna start with this u plus v, so I'm just gonna write out what that side is. So this is gonna be 2u plus 2v all the way down, 2v. And then I need to add that to this w. So now, if I add these together, what do I get? I will ultimately get something of the form 2u plus v plus w. I'm kind of skipping that step in the middle where I need to factor out the 2. But you can see, right, that this and this are clearly equal. So this axiom holds, is what we would say. So we would state that, you know, after all this, so axiom, let's see, 3 holds. So I'm running out of space here. Okay, so let's keep going. All right, so up next, I need to define what the 0 vector is. So in this case, my 0 vector is just going to be actually zeros. This is totally fine. It doesn't violate the form because you can rewrite this, right, as 2 times 0. It still fits the form. It just ends up equaling 0. So we have a 0 vector. It's still an Rn. Since n is allowed to be anything that we want, as long as I can just multiply that by 2, we're good to go. So we've got 0. So and then you can notice, of course, you can do this, but you can do u plus v is going to equal, or sorry, u plus 0 equals 0 plus u. So I'm going to omit the proof here because I've been doing a bunch of the addition, but 0 plus anything from u is going to just end up back in u. So this one definitely works. Okay, so we are 4 down. And so let's see. So let's prove, let's see, I've got to do 5 here, so I have to show that for each u and v there is a negative u and v, so we'll show that that exists. I'm going to just do, for the sake of keeping this video short, I'll do axiom 7, and then 8, 9, and 10 will be up to you to prove, because this will be a vector space. So this is not a, this vector space is not a problem. So okay, so now I need a negative u, so let me clear some space again. So I have to show that there will be a u plus a negative u, and that will equal my 0 vector. So in this case, I can just define my negative u as just the negative of whatever my u's were to begin with. Because again, this just has to be of this form 2 times x, as long as an x can be any number. So this is going to equal negative 2u, negative 2u, so we have that. So then you'll notice, so if I take u plus negative u, so if I add those together, what do I get? I have 2u plus negative 2u all the way down. And so this will just end up equaling a whole bunch of zeros. So this is what I wanted to fulfill. So we're good to go here. And now I'll do that last axiom, so I'll make some space again. So for that last axiom, so I've got k times u plus v. So I need to show that this equals ku plus kv. So okay, let's start on one side. So if I start on this side, so what is this going to look like? So I'm going to have k times this 2u plus v all the way down. And so then if I distribute the k in, this really ends up equaling k times 2 times u plus v, so on and so forth, k times 2 times u plus v. Okay, so now let's distribute this. So within each n-tuple, this becomes 2ku plus 2kv all the way down. And then, now notice, let's see, 2kv, okay. So now I've distributed that all the way down. So now what I'm going to do is I'm actually going to break each one of these up into the u's and the v's. So I can break this up into 2ku all the way down. So I've just got the vector of the u's and then just the vector of the v's. And then I can factor the k out of all of those, like so. So let's see, 2v, 2v. And so what does this ultimately mean then? This means that I have ku plus kv. So I started on this side and I ended up proving this side just going through the operations. So that axiom holds. And so you do a very similar amount of work for the last axioms, but this will be a vector space. So you do have to show all the axioms hold. It's not the most exciting thing to show, but I would recommend that you prove the last ones just for completeness. Okay, so I want to now move on to just a couple more. So this last set, so I have the set of all pairs of real numbers of the form xy, where x is greater than 0 with these standard operations on R2. This is not a vector space, and the reason why is we have this constraint on x. So the thing is, so it's definitely closed under addition. So let's say that I have my u is going to be, so u1, u2, and my v would be equal to, let's say, v1 and v2. So the thing I know about this is that u1 and v1 have to be greater than or equal to 0. u2 and v2 can be whatever, but I have this one constraint. So I'm fine for adding these two vectors. Adding two positive things together is going to stay positive. So axiom 1 is fine. And multiplying positive things by a scalar is also going to be fine. So these are not the issue. So axioms 1 and 6 hold. But where we are going to run into an issue is, so we do have the 0 vector. So we have 0, 0 is going to be the 0 vector. The issue though is, so actually let me clear some space. So I know what my 0 vector is in this case. So if I add 0, 0 to either one of these, I will get back to these two vectors. The issue is, what would my negative u be? Because negative u, so if this is a positive number, I need a negative u to get a 0 with this. So there is no negative u. This does not exist since u1 is always positive. So that means that, let's see, which axiom was that? That was axiom 5. Axiom 5 fails. This is not a vector space. So sometimes it's easy to pick out what the axiom is that fails. In this case, I think it was more straightforward because we had this big hint, it has to be greater than 0. As you can see, there are other times where it's not as obvious which axiom is going to fail, and you might end up having to go through a bunch of the vector space axioms to figure out which one fails. So you're just gonna have to stay on your toes. If you found this video helpful, I'd love if you hit that like button or that subscribe button. And so I'm going to leave this video there. I think it's gotten long enough, and I'll talk to you guys in another video.